Hello everybody, Dave here, and today we're going to do our second lesson in uniform circular motion, and today we're just going to deal with a couple of really important applications of the topic. Hopefully you've already watched the first lesson and you understand a little more about centripetal acceleration, centripetal force, and how those really play off of previous understanding of physics in dealing with Newton's laws, and how certain scenarios can be treated differently depending upon the orientation of the object relative to the horizon. So today we're going to take a look at the different applications that require a little more thought than just vertically up and down. And so again, this is not a comprehensive list, but I do my best to give you examples that really kind of hit the major types of problems that are seen in this subject. So again, bank corners dealing with NASCAR racing, toy airplanes, which are things that are spinning around in a circle hanging from a string, dealing with just revolving objects above your head. My class does a lab I call the cowboy lab, which is a object on a string, and instead of spinning it vertically, you try to spin it horizontally over your head, but obviously it's not going to be perfectly horizontal. And then the final one is one that's always a good one, which is dealing with artificial gravity problems, which is the answer to the question of why do they have space stations spinning when they're in space? So first, let's deal with bank corners. And when we're dealing with bank corners, you may not realize this, but when you look at a racetrack, especially NASCAR tracks, they actually have corners that are banked at a pretty steep angle. This angle here is 31 degrees. And the reason for that is pretty straightforward. They're trying to make sure that the car doesn't skid. So if we take a look at the free body diagram of this car, you can see that we have a normal force that is perpendicular to the bank surface. This is something that you dealt with when we had inclined planes in grade 11. We have the force of gravity, which is pointing straight down. And then we've also labeled some components of the normal force, which are going to be important later on. Now, please remember that when we deal with free body diagrams, they do not include the components of a force as part of the diagram. Notice how I've drawn them in dashed lines, but even still, it is more appropriate to not draw those at all. But you'll notice that in this case, I actually have the normal force a little longer than the magnitude of the force of gravity. This is different from when we dealt with inclined planes, and the reason for that is because we have a circular path taking place. Remember that we are a banked corner, so as we're traveling around a corner on this slope, there is still a circular path. And that circular path is actually going to be parallel to the horizon, so not the surface itself, but the actual horizon, or just the flat line. And that is pointing towards the center, as you can see with the label of A. Well, that's interesting, because with the vectors that we now have, we can directly calculate the centripetal force, because we could simply do some vector addition and take the normal force, add it to the force of gravity, and that's going to give us this horizontal component, which I've labeled as Fn sine theta. But because the centripetal acceleration is pointing in the direction of that component, folks, that is the only force responsible for it maintaining its path. And so when we go to calculate centripetal force, we're going to use Fn sine theta and not something else. So this is the important part here, is to recognize that we have some vector addition that we can do. There could be some Pythagorean theorem type stuff involved to actually find the magnitude of the branches of the triangle. Just be careful in the way that you label things and make sure that you're clear on where the angle comes from. So let's take a look at a classic example. And we have here this Daytona International Speedway in Daytona Beach. We have this car here, and it's a 31-degree bank corner, and we have its maximum radius of 316 meters. And what we're trying to find out is the centripetal acceleration so that the banked car won't slip up or down the incline. This is a classic question to ask when we're dealing with bank corners, and then, of course, find the speed of the race car itself. So the first thing we have to recognize again is that we see Fn that is going to be perpendicular to the bank surface. We see Fg that's pointing straight down, and it's important that we understand where the angles are at play. When we talk about the angle of a bank, it's always from the horizontal up. If it's labeled anywhere else, make sure that you correct that accordingly. So for A, the first thing we need to do is we need to be able to draw this vector triangle. And so again, we're doing vector addition because we have the normal force and we have Fg. And we know that the final component of this right triangle is going to be horizontal to the horizon, pointing towards the center of the circle, and that's going to be Fn sine theta. Well, that's fantastic, but we don't have a lot of information yet. You'll notice that the question didn't give you the mass. In physics, if the question didn't give you the mass, chances are it cancels out somewhere. So let's see if we can figure out where that is. We know that centripetal force is going to be this Fn sine theta, and we know that it's always equal to mv squared over r. Well, we also know that we can find Fn using some simple trig, because we know that the cosine of theta, the way that we've labeled it, is going to be Fg over Fn, and so Fn is just going to be Fg over cos theta. And so when we substitute in this quantity for Fn into our equation for Fc, I did a quick substitution of tan theta is equal to sine theta over cos theta to give you that it's mg tan theta. Well, that's still equal to MAC. Well, guess what? Look what happens to the mass. The mass cancels on both sides, and since all we're looking for is a centripetal acceleration, we can just find it using centripetal acceleration is equal to g tan theta, plug in our values, get our answer of 5.89 meters per second squared. So this is a great question in that it shows you that you don't need the mass to be able to solve problems, but you certainly need to know how to set them up according to what quantities we have, what quantities we need, and the conceptual understanding of what's going on physically with this object. Obviously, once we've found the centripetal acceleration, the rest is fairly straightforward because we know that centripetal acceleration is equal to v squared over r. We can plug in our AC, we can plug in our r, and we can go ahead and get our speed of 43.1 meters per second. Here is a nice little hint for you when it comes to AP stuff. You always want to make sure that no matter what answer you get for the previous question, you have to follow through and use that into the subsequent questions after the fact. So even if you weren't sure that your centripetal acceleration was right, if you can show conceptually that you would have used that appropriate value to calculate the speed, very often you're going to get a good amount of credit, if not the full credit, for understanding that there was a tie between A and B. So please make note of that as you work through these problems. For example 2, we're going to do an amusement park ride, and this is going to be, it's called various things. It's called the gyrotron is the one that I remember it the most as. But again, the whole idea is that it spins in such a way that you are essentially plastered to the sidewall. And the question that it's asking for here is what minimum coefficient of friction is between the rider's clothing and the wall in order for the rider to not slide up or down. And so this question is all about the picture, and it's understanding that we have a circular path, and because of that, our person is actually going to be plastered up to the wall. Remember, the reason they're up on the wall has nothing to do with force, it has everything to do with inertia. But it is still interacting with a surface, which means that there is a normal force pointing perpendicularly from that wall. This is your aha moment for a question like that. Because now that we know that you're not moving up or down, so because you're static, the force of friction that's pointing up to counteract the force of gravity pointing down have to be equal to each other. This is your big moment, because now we can find Fn using the speed of the rotation, which we were given as 15 meters per second. You can plug that in to get your value for Fn, and then you can use that Fn to calculate Ff, which will allow us to figure out what the coefficient is. And so you can see in this question here, we've set it up so that we know that Fn is equal to Fc, we know that Ff is equal to Fg, we've substituted everything together before we plugged in values to get our answer of 0.13. Now, one thing that's important for you to develop is this skill. The ability, instead of always calculate, take your concepts, take your equations, put them all together into one nice equation by which you're going to be able to solve for whatever quantity you're looking for and then substitute the values in. It is going to be much easier for you to track a mistake that you've made if you don't substitute answers in until the end, because it's a lot easier to track variable mistakes than it is to track calculation mistakes. So that's another classic right there. Let's see if you now know how to do a question like this. We're going to say that the gyrotron at Daveland can be modeled as a rotating cylinder with a radius r. And what I want you to do is I want you to derive a formula for the period of rotation t in terms of r, g, and mu. What I would encourage you to do is press pause now, give the derivation a try. It sounds very similar to the question that you just did, and then we'll see if you can get it right. So this question requires you to remember one thing, and that's the fact that you're traveling at a constant speed. And you know that because you're traveling at a constant speed, speed is equal to distance over time. But because it's a circular path, the distance that you're traveling is equivalent to the circumference of the circle itself, which in our case is 2 pi r. Notice that I used a capital R. I have to use the terms that they gave me. So don't use small r's, don't use any other language to describe this radius, just use it as a capital R. And that's going to be divided by the time. Well, remember that the period of rotation is defined as t, so we substitute in the small t for the capital T, and now we have an equation for a constant speed of rotation. This is something you're going to see again in rotational motion, so it's certainly worthwhile knowing now. Now we understand that because the person is held motionless in the side, our F net is equal to 0. Because of that, we go through the exact same process that we went through last time. We go ahead and we find out that Fc is equal to Fn, which is still mv squared over r. But now this time we're going to substitute in our quantity for v as 2 pi r over t. Now you'll notice there's a lot of squares and whatnot going on there, and that's because 2 pi r over t squared is 4 pi squared r squared over t squared. One of the r's cancel, and you get m 4 pi squared r over t squared. This is another classic representation of the equation for centripetal force. We also know that because the person is motionless on the sidewall, that FF is still equal to FG. We can plug in mu Fn is equal to mg, and now we have the equation that we need to solve for t by substituting in our equation for Fn into the equation for the force of friction, and we get our final equation of t is equal to the square root of mu 4 pi squared r over g. It's important that you get used to this type of derivation, and it's important that you get used to understanding that the notations matter. It is telling you that it is in terms of capital R, capital T, small g, and mu. That means don't use any of your other information that you think you can use. Don't redefine these as anything else. Always make sure that your final answer has these quantities in them. Best of luck to you, folks, and we'll see you again.